functions and relations today. So get those phones away, earbuds, etc. So first of all, what's a relation in math? A relation, very simply, is just a way of relating inputs and outputs. That's it. So a bunch of ways we can do that. And if we look at ordered pairs, the input is the x value, the output is the y value, right? Bunch of different ways we can express relations. We could use a set of ordered pairs. That's one way to do it. We can use, so there's a set is one way. We can use a table. We can use a graph, or we can even use this weird thing called a mapping. And we'll look at examples of each of those four things today. For a relation to be a function, there's an additional little rule that we're going to introduce here in just a little bit. So relations are very broad, functions are more specific. All functions are relations, but not all relations are functions. In the same way that all Siberian Huskies are dogs, but not all dogs are Siberian Huskies. Okay, so function or relation, we need a way to talk about the set of the inputs and the outputs. What do we call the set of x values, or more generally, the set of all inputs? They don't necessarily have to be x values. It starts with a D. No. Domain. Domain. Okay, so that's the set of all inputs. The set of all outputs, or y values, doesn't have to be y values, could be other values, but the outputs, what do we call that? The range, yeah. Okay, and it's easy to keep that straight because the relationships are always alphabetical. Whether we're talking about an ordered pair, x, y, x goes before y, input versus output, I goes before O, domain versus range, D goes before R, right? So all the first things alphabetically go together. So the blue list goes together, and the second things alphabetically, the red list, they all go together. Yes? No, it just accidentally. Yeah, but it's a good way to remember it. Yeah. So a relation with a distinct set of points would be like a scatter plot. We call that a discrete relation, whereas a relation whose graph looks like connected lines or curves is a continuous relation. Okay, and we'll look at both of those also. So then, how does a relation become a function? Well, here's how. A relation in which each element of the domain is paired with exactly one element of the range is a function. In other words, here's an easier way of stating that. A function is a relation where each input has exactly one output. You've probably heard it that way maybe in the past. Okay, so that's a function. Here's an example of a function. Okay, how many input values are there? What are they?
They're ordered pairs.
Okay, but what are the input values? What's our domain? 1, 2, 3, 4. Yeah, good. The x values 1, 2, 3, and 4. The output values are 9, 8, 7, and 12, right? But notice that each input has exactly one output. If I input a 3, I'm only getting one output, which is 7. And that's true for each of the 4 inputs. So that is a function. This is not a function. Tell me why.
Oh, 3 points. It's because there's more than one the same number.
Okay. Yeah. What's the input that causes problems here?
The 1.
The 1. There you go. 1 is problematic because if I input a 1, I can get a 9 or a 12. So it fails that function test. Each input does not have only one output. Yes, sir.
Is it a function if multiple inputs have the same output?
Yes, and we'll see that in a little bit. Good question. Very good question. So what does this correspond to graphically? So if I've got a bunch of points with different inputs and each input only has one output, then those points are not going to line up vertically. None of those points would line up vertically. If I have multiple points with the same input, well, how are those points going to line up? The points with coordinates over 1 and up 9, and over 1 and up 12. How do they line up? Vertically, yeah. And because they line up vertically, it's not a function. So that gives us what's called the vertical line test. In order to be a function, a vertical line cannot pass through more than one point in the graph of the relation, if it ever does. If a vertical line intersects the graph in more than one place, then it fails the vertical line test and we know it's not a function. Okay? So here's an example of a function. Would be something like, let's say, a parabola. Okay, that works, right? Vertical line would only ever intersect that in one place. But here's an example of a function, a different kind of parabola. Sideways parabola, it wouldn't work, would it? A vertical line would intersect that in more than one place, like there's an example. So it's not a function, okay? And just a couple more quick examples of that, just real quick. Give me thumbs up or down. Does this pass the vertical line test? Yes, it does, okay? How about that one? Thumbs up or down? No dice. There's a problem, right? How about this one? Where's the problem? Where? Oh, right there. How about, huh? There's where 2 points line up vertically. So no, that's not a function. So let's now just look at some examples of different ways of expressing relations. And what we want to do here, I got to get a drink, man. So here's using a set. These are just sets of ordered pairs, right? So we've got a set of 1, 2, 3, 4 ordered pairs. So I want you guys to tell me what the domain and the range are, but I got to tell you something about that first. The domain is going to be the set of all the x values, right? When we're writing out a set like that, we want to always put the set, we want to write the elements in numerical order, increasing numerical order. And the reason for that is if we have a really big set, we don't want to have to like randomly scan through the whole thing to see if a specific number is a part of that set. If it's in numerical order, we can always go check really easily and quickly, right? And we also don't write repeated values down. If a number shows up more than once, we only write the number down one time. In other words, we're just writing the list of all the different numbers that do show up in the domain or the range. So what's the domain then? First number we would write would be -1, then 0, then 4, then 6. Okay, how about the range? -2, 3. Good. Up, thumbs up or down? Function or no? Yeah, it is. Good. That works, doesn't it? Okay, how about this one? Domain? 8. That's it. Okay, right? Okay. How about the range? What's the smallest? No. -6, 0 to 4. There we go. Okay. Thumbs up or down? Ah, good. No dice, right? And the reason we have an issue is right here. We get the input 5 gives us two different outputs. You guys probably could have told me, even just looking at those sets, there was going to be an issue. How come? Okay, but even if you didn't see the original set, if I just looked at the domain and the range, you probably could say, okay, that's not going to work. Yeah, there's 3 elements in the domain and 4 in the range. So doesn't that imply that at least one of the domains is going to have to connect to 2 outputs, right? Yes, sir. It's just a relation, just a non-function. It's a relation that fails to be a function. Just like a Cocker Spaniel is a dog, but it's not a Siberian Husky, right? Okay, make sense? You like my dog analogies? Okay, good. So no, not a function. So those are tables. Here's an example, or those are sets. Here's an example using tables. Now these are T tables. T tables, you can write tables horizontally, but those aren't as good. vertical tables are better, and we call these T tables because that makes a T, right? And the reason these are better is when I read them horizontally, they look like ordered pairs. Isn't that nice? So it's easy to graph stuff from T tables. So the domain's just the X column, domain's the Y column, right? So how many elements in the domain in this first one? 4. Yeah, and they'd go in that order, right? If I rearrange them in numerical order, there you go. How many elements in the range? 3. Okay. See, -8, -1, 3 in order. Okay. Function, yes or no? No. How come? Okay. Well, let's do a little test here. You guys tell me with your fingers, how many outputs are there for each of these inputs? How many outputs are there for 7? How many different outputs are there? I input 7, how many different I only get 1. If I input 7, what's my output? -8, so I get 1. So that's 1 finger. How many outputs for the input 2? What are they?
3 and 3.
No. I only get 3. Everybody see that? If I input a 2, the output is always 3. 1 input, 1 output, right? So again, input a 2, I have 1 output. How many outputs for the input 0? 1. And it is -1. How many outputs for the input -4? 1. So is it a function? It is. It passed the test. Each input only has 1 output. So is it a problem that we get multiple numbers that are the same in the output column? No, it's not. It's only a problem. We only have an issue if we have repeated values in the domain, right? If x values do not repeat, it is a function. If x values do repeat, we've got an issue, right? So this was actually okay. Whoops. This was actually okay. This is a function. And then this one, clearly that one is a function, isn't it? Each input only has 1 output. Okay, how about this mapping here? What's a mapping? Well, we've seen stuff kind of like this. It sort of looks like a Venn diagram, doesn't it? It kind of looks like the set diagrams we used when we talked about the sets of real numbers, right? So this blob right here just contains all of the input values. That's the domain. This blob contains all the output values, so that represents the range. How many values are there in the domain? What do you think? How many values are in the domain? No. So you guys need to probably turn around and pay attention, huh? Yeah. 3. 3 values in the domain, and they are, there you go, -4, -2, 5. How many values in the range? 4. Okay, is this a function? Thumbs up or down? How come?
Because there's 3 in the domain.
Okay, true. There's something else about this mapping that just makes it really obvious right away we got a problem. Yeah, look at that. There's 2 arrows leaving the 5. Okay, that's an issue.
So that's 5 twice.
So this is not a function, right? Because again, let's do our little test. You guys hold up the number of fingers that each input, the number of outputs each input has. -4, how many outputs? 1, good. -2, how many outputs? 1. 5. 2, up there it's not a function, right? Because we held up a 2. Okay, make sense? Okay, because there are 2 outputs for that input, it is not a function. How about number 6? We don't even worry about the domain and the range. Is it a function? It is. We can tell right away. How can you tell immediately that it is a function?
Each number has only 1 output.
Yeah, there's only 1 arrow leaving each input. Over here we had 2 arrows leaving one of the inputs, which was a problem. And probably some people looked at this and had to think a little bit. I understand. That's okay. It's okay if 2 arrows land on the same number in the range, as long as every arrow only leaves 1 element in the range. Domain, sorry. Huh. Each element. That's right. Yes.
It's okay for the range. So I could have 2, 7.
Yes. Exactly. Exactly. So in a mapping, two arrows can point at the same number, but two arrows can't leave the same number. Okay? So how about this guy here? This is a graph, right? So this is the other way of writing a relation, and it's not a function, is it? We can see it's not because we have 2 points that line up vertically. So we can already tell it's not a function. Now, if we want to write down the domain here, I want to write all the x coordinates in order. How should I scan that graph to get the x coordinates in order? Left to right, exactly. So what's the leftmost x coordinate? -3. Next one, 0. Next one, 2. Last one, 4. Okay. How about the range? How would I scan to get the range in order? Bottom to up, bottom to top, right? Yeah, bottom to top, because y goes upwards is positive. So the bottom y value would be -5, -2, it looks like, -1, 1, and 4. Okay, good. Okay, so what about something like this now? This is a continuous graph. How many points are graphed in number 7? 5. 5 total points. How many points are graphed in number 8? Infinity, absolutely, because it takes an infinite number of points strung together like beads on a wire to create the line. Agreed? Every time the ant takes a little bitty step, he lands on a different point with different coordinates, right? And there are an infinite number of those packed together. I didn't mean to do that yet. Whoops, I guess I gave it away. What's the domain here? Can you see why it's all reals? Because the domain represents all of the x values that are graphed on that line. Don't the x values run from -infinity on the left to +infinity on the right? Okay. How about the range? Again, they're going to run all the way down from -infinity to +infinity because the line goes forever, right? There's another way of thinking about this that's kind of cool in math. We can use the concept of a projection. So a projection means if I want to project all the points on that line onto the x-axis, that's going to give me my domain. So for example, this point right here, if I project it, squeeze it vertically onto the x-axis, so it's not going to move horizontally, but it's going to get squeezed down vertically, this point ends up projecting there on the x-axis, right? This point projects there. This point stays put. Right? But if I did that for all the points on the on the line, wouldn't those cover the entire x-axis? So did that make sense? If I took all the infinite points on that line and projected them onto the x-axis, they would cover the entire x-axis because the line goes forever. Agreed? So when I do that, I'm just creating a graph of the domain. So the graph of the domain is all reals. Same thing with the range. If I projected these points onto the y-axis, that point would project there, this point would project there, that point would project there, and so on. And I would graph the entire y-axis. Agreed? So I get all reals. You guys have done projections before without knowing it. Well, when you do a projection, technically when you do a projection in math, you're going to keep all the data, but you're going to project it onto a different, express it in a different way. What are some ways that you could take a three-dimensional system and project it onto a two-dimensional surface? You guys have probably done this a lot. Yeah, that's actually true. Then you're going from 2 dimensions to 3 dimensions. That's true. Um, Another one is just looking at a topographical map. If you look at a topographical map, the east and west positions don't change. Those stay the same as they would on the surface of the Earth, right? But you're also given information not only about how far east and west you are or north-south, you're also given information about how vertically how far up or down you are relative to sea level. How is that given to you on a topographical map? Who's like when you've gone hunting or something, you've probably looked at these things, right? Yeah, the lines. Yeah, does that make sense? The lines of elevation. Okay, so the lines of elevation, those numbers on there are telling you the information about how far you are up vertically. So essentially what you've done to create that topographical map is you've taken a relief map, like the Earth, and you've just shrunken that down, and then you've squashed everything down onto a flat piece of paper. But as you've squashed it down, you've encoded the heights with the little numbers on the map. So all the information's still there. It's just two-dimensional instead of three-dimensional. So that's a same thing, right? That's just what we did here, but on a little more sophisticated example. And you can do more of that, like if you go on and study math in college and you do multivariable calculus, you'll do a lot of that stuff where you'll do these conformal mappings where you'll take three-dimensional surfaces and project them onto two-dimensional surfaces, and it's pretty cool stuff. So is this a function? Yeah, it is. Passes a vertical line test. Yes. Okay, real quick, just one more last example of this. Function or no? Thumbs up or down? Yes, it is. Each input only has one output, so yes, it is. The outputs are all the same, so how are those points going to line up if the y coordinates are all the same but the x coordinates are different? Yeah, they're going to line up horizontally, aren't they? So therefore, it makes sense that that is a function because they line up horizontally, they still pass the vertical line test. But what about this example? No, right? That's not a function. And if I were to graph those 3 points, how do you suppose they line up? Vertically. So they fail the vertical line test. So it's all, the more you study math, the more these are like the cool little light bulb moments where things just come together, where you realize, wow, this is all totally consistent. I mean, this stuff, we learned, we use different language to talk about this stuff, but it all works the same way, right? It's all logically consistent. Okay, what about these? Let's look at some different, little bit tougher graphs. How about this guy over here? What's the domain of this thing? Domain is the set of all the x values. So if I had to write using interval notation, all of the x values, yeah, there's my comma. What's the number going to be to the left of the comma? What's the bottom edge of our domain? -4. Exactly, because of this point right here. Everybody see that? Because there's a point where the ant can't go any further to the left, right? So the coordinates of that point are -4, -1, right? Well, -4 is the bottom of our domain, isn't it? Make sense? If I were to project this entire thing onto the x-axis, wouldn't that just give me something like that? Agreed? Okay. So what do I put with the -4 then? Parenthesis or bracket? Bracket, because the ant can stand there, right? -4 is an x value that is on our graph. So we get a bracket. What goes to the right of the infinity? Yeah, because it goes forever to the right. Okay, how about the range? What goes to the left of the parenthesis? So the -1 is as far down as the ant could ever go? Negative infinity, because the ant could continue to travel down this way, and that line's going to slope down forever. So the ant will always continue to drop lower and lower as he walks along that line, won't he? Forever. So negative infinity. How about the upper limit? Infinity, because he's going up forever, isn't he? And what has to go with infinities? Parentheses or brackets? Parentheses. Okay, is this a function? No. And here's my proof. It's not a function because it violates the vertical line test right there, for example, right? I mean, we could pick any place, but that's a convenient place on our graph. There are 2 points that line up vertically, so no. Make sense? Okay. How could I say the orange domain using inequalities instead of interval notation? X is what? Greater than or equal to -4, exactly. How about the range? Well, I can't really say that using interval or inequalities, can I? It's just all reals. Okay, how about over here? What about this guy? Same thing. What's my domain? -2 is my bottom limit because the coordinates there are -2, 1. What's the upper x value? 5. Yeah, because the coordinates are 5, 1. So I go -2 to 5, parentheses or brackets? Brackets, because those are values on the graph, right? The ant could stand at that x coordinate or that one, okay? How would I say that using inequalities? X is what? -2 and good. Okay, how about the range? What's my left number? Say it again. -2, yeah. Because right there is a point that has a y coordinate of -2 and 4, because there's a point that has a y coordinate of 4, right? Parentheses or brackets? Brackets. Okay, is it a function? No, definitely not. Okay, how about these guys? This one, so this is a parabola, right? We don't know how to graph parabolas at this point. Eventually, we'll know how to do that pretty quickly. But for now, we'll just graph this thing on Desmos, and that's what we find. Desmos is useful, or a graphing calculator is fine too. A TI-84 would do the same thing. If we pick that top point, it'll even tell us on either a graphing calculator or on Desmos, it tells us the coordinates of that vertex, which is just the highest point here, right? So based on that graph, what's my domain? What are the x values included? -infinity to infinity. The graph doesn't stop there, does it? Right? Everybody get that? If I zoom out on Desmos, Blake, you guys are up here, please. Focus up here. If we zoom out on Desmos, the thing just keeps getting bigger and bigger, right? The more I zoom out, the more this parabola is going to spread out to the left and the right, infinitely, okay? So yeah, this thing goes forever left and forever right. And so the domain just looks like that. Okay, now what about the range? Can anybody tell me a number that's going to go? And where does 3 go? To the left of the comma or the right? To the right. No, on the right. How come? How come the 3 has to go there and not there? Okay, good, because the 3 is, remember, what goes on the right is going to be the upper end of that set, or of that. Does that make sense? So the range has a top value of 3, but the bottom value is what? How far down does this graph go? -infinity, right? So -infinity has to go on the left because that's the bottom. 3 goes on top because, or goes to the right because that's on top. Okay. Parentheses and then bracket or parenthesis with the 3. Bracket, yeah, we are including it. Is that a function? Yes. Okay, last couple. Really simple ones. How about this line y equals -7? Okay, you guys all remember from previous years when you have y equals a number or x equals a number, show me with your arms, what are the two types of lines we're graphing? Vertical and horizontal, right? Which one goes with which? Think what this is saying. This is telling me that the output y is -7 regardless. It's always -7. So if the output is always -7, the y value, input could be anything. What kind of line am I making? That's horizontal, isn't it? Right? Because all the y coordinates are -7. That never changes, so it has to be horizontal. There's a tricky way to remember this. when you have y equals a number, the math gods are just telling you the y-intercept, right? So if that's the y-intercept is at -7, was it there? I don't know if I counted right, but I think that's 7. 7. Well, then what kind of a line has a y-intercept, a horizontal or a vertical? Got to be horizontal, right? A vertical line doesn't intersect the y-axis at all, right? So it's got to be horizontal. There's my line. So what's the domain? All reals, yeah. It goes forever to the left and forever to the right. Okay, what's the range? No. -7, period. There's only one output value and it's -7. So the range is, like, really technically we could say something like y equals -7, but if I want to write that as a set, it's got to be a discrete set, not an interval, right? It would just be in set brackets, just one value, which is -7, okay? Is that a function? Yes. Well, what do you think this is going to look like? X equals -1. So okay, but what's the graph look like? It's got an x-intercept of -1, so it's got to be vertical. So what's the domain? And I got to write that in set brackets. There's only one discrete value. The range? Okay, is that a function? No dice. Vertical line obviously fails the vertical line test. Okay, that's good for today.